Hi folks, welcome back. So you've come into the hydrolysis unit here on Bennett's Chemistry 12 tutorials. So far I have done a couple of videos, 3 videos on hydrolysis, and then there was a whole series before for the acid-base unit. If you've been here before, you'll know kind of what my intention is for these videos. These videos are acting as a replacement for classroom instruction in case you're at home because school has been shut down and everything's been online for the COVID pandemic. So this is designed to get particularly Chemistry 12 students in British Columbia because I'm a teacher in BC, so I follow that curriculum. But let's face it, I mean, Chemistry 12 is Chemistry 12 probably. Even if you're doing chemistry in Georgia, you're probably covering very similar topics, maybe emphasis slightly different one place or another, but generally speaking, we're all kind of talking the same thing. So today's class it's a little bit of a deviation from what I intended to do. What I intended to do was the anhydrides today, and then I was going to do a little bit of a beginning section on the predominant Bronsted-Lowry reactions. However, I've changed my mind. I'm going to make this one thing. It'll probably be fairly short then, but I'm going to make it its own little separate video, and then the next one will be anhydrides, and then I'll just focus solely on what those things do when they chemically react with water. Okay, so today, what I want to do, you can see up here on the board, I've got, so if you're talking about an ionic compound or a salt and you dissolve it into water and it dissociates into its 2 ions, the whole concept of this unit has been how can we tell or how can we predict whether or not the solution that results from dissolving that salt will be acidic, basic, or neutral? And can we determine, relatively speaking, maybe you've got 2 salts dissolved into 2 separate solutions, which one might be more basic than the other if they were given equimolar concentrations? So that's kind of the underlying theme of this. Hydrolysis being the chemical reaction with water. While some ions, when they're floating around, they don't just float around and do nothing. They actually act as acids or bases. And so they either produce hydronium if they're an acid or hydroxide if they're a base. Therefore can make the solution acidic or basic, even though they were just an ionic compound. They didn't kind of fall into that traditional Science 10, Chemistry 11 definition of what an acid or a base would be. Okay, so today there's kind of 2 things. Number one, how do you know when you've got more than one choice? Okay, so a predominant reaction, well, predominant kind of means one is happening more than another. Predominant does not mean exclusive. It doesn't mean it's the only one going on. Predominant means there are other things and one is dominating over the others. And so in chemistry, when you're talking about the predominant reaction, it means there's at least 2 different reactions going on, and one of them is happening at a higher frequency than the other one. Therefore, it's the predominant reaction. So we have to determine, when is that situation even occurring? When is there more than one Bronsted-Lowry reaction even going on in solution? And how do we tell which one is predominant, which is the second question. Okay, so can you, given the choices, what are the choices first of all, and then how do you actually go ahead and determine which one's the predominant reaction, and also what is the equilibrium constant for that predominant reaction? And I guess really it's the equilibrium constants that are going to provide some proof for us. So if someone says provide some proof that that is the predominant reaction, well, your proof is the equilibrium constant, and the one that favors products over reactants. Okay, so the larger the value of the KAQ, it's going to be the predominant one. It's happening at a higher frequency than the other ones. Okay, so let me kind of get through this because it's fairly straightforward. So first thing I want to do is I want to give an example of something where there are not choices. There's just one Bronsted-Lowry reaction. So let's start with a salt. I'll give we'll go with, let's go with potassium. Let's go with potassium sulfite. Okay, so I'm going to take some potassium sulfite. It's in solid form. I dissolve it into water, and it's a soluble compound, and it makes two. Oh, let me erase that and do it properly. It makes two potassium ions and a sulfide ion. And going through our thinking, our decision making for whether this is acidic, basic, or neutral. The potassium is not one of our three ions, iron, chromium, or aluminum plus 3, that will form complex ions and then act as a weak acid. It is not ammonium, NH4 plus 1, or an amine that has an organic compound with an NH3 plus 1 group. And so therefore the potassium ions are spectators. The potassium is a spectator ion. The SO3 minus 2 is the anion. Does it have a donatable H? Was our first step in our decision making. The answer is no. It doesn't have an H on the left, so it doesn't have a donatable H. If it doesn't have a donatable H, you then ask the question, is it the conjugate of a strong acid? And you have to be careful because sometimes formulas are fairly close, so you have to pay really close attention. SO3 minus 2 is not the conjugate of a strong acid. It is not one of those 6 up at the top of the Ka table that do not act as bases. So this is the conjugate of a weak acid. So if that's the case, if this is the conjugate of a weak acid, this thing acts as a base. Now, it is a base and only a base. Like there was no question as to whether or not this could ever be an acid. It doesn't have a donatable H. The potassium was a spectator ion, couldn't be an acid or a base. And so therefore, you've only got one possibility. The SO3 minus 2 acting as a base is the only possibility. There is no choice. So the predominant Bronsted-Lowry reaction is the only Bronsted-Lowry reaction. And so this guy would proceed in water It's a weak base, and so it picks up an H and leaves behind hydroxide. And so that would be your predominant Bronsted-Lowry reaction. That value right there would simply be the Kb of SO3 minus 2, which is equal to Kw divided by the Ka of its conjugate, which is that chemical over there. So the conjugate acid is HSO3 minus. I'm not going to do the math because the math you can just take off the table and you can actually come up with that value. So there is no choice there. SO3 minus 2 is the only thing doing a Bronsted-Lowry reaction. So of course it's the predominant one. So no choice, you don't really need to determine whether there's a Bronsted-Lowry reaction there or not. Now there are two situations where there is a choice. Okay, so I'm going to change this up a little bit. So what would happen if, let me change this ever so slightly. Okay, so here's our first example of a chemical where there is a choice. There are two Bronsted-Lowry reactions that are going to go on, and there is a predominant one and then a less dominant one, obviously. Okay, so what are the two possibilities here? Well, K plus is still a spectator. Okay, so that's not what I'm changing. However, the HSO3 is, if you go through kind of the process, does it have a donatable H? Yes. Is it the conjugate of a strong acid? No. HSO4 minus would have been the conjugate of a strong acid. This is HSO3 minus. So hydrogen sulfite. And so because this thing is not the conjugate of a strong acid and it's got a donatable H, that means it's amphiprotic. And if it's amphiprotic, that means it can act as an acid or a base. Now, it's not really, well, individual molecules are or. But if you're talking about trillions of these things floating around in water, there will be a whole chunk of them that act as an acid, but another chunk of them that act as a base. And so it's not as if they cannot do one once you determine the other one's a little bit more powerful. Both of those reactions are happening. So let me write down HSO3 minus acting as an acid. So HSO3 minus as an acid would be weak acid, forms hydronium, and SO3 minus 2. So the HSO3 minus would donate an H to H2O, it would form hydronium, and SO3 minus 2. That has an equilibrium constant, which is that thing's Ka. So I pull out my table, and I just look up HSO3 minus, and it's 1.0 times 10 to the negative 7. Okay, just reading that right off the table. HSO3 minus, though, could, because it's amphiprotic, also act as a base. So as a base, HSO3 minus plus H2O goes to, picks up an H and forms hydroxide. Now that has an equilibrium constant because that is HSO3 minus acting as a base. So that has an equilibrium constant equal to K. It's Kb, which will be Kw divided by the Ka of H2SO3. So I now pull out my Ka table because I need an actual value here. If I'm going to actually prove this thing, what it's going to be, acid or base, I need an actual number here. So Kw is 1.0 times 10 to the negative 14 divided by H2SO3 is really high, 1.5 times 10 to the negative 2, which is 6.7 times 10 to the negative 13. And so it has HSO3 minus has a higher Ka than its Kb. So it's easier for it to donate an H than it is for it to accept an H. Its Ka is bigger than its Kb. So the predominant reaction is the one that favors the products the most. So this one has the higher KEQ value, which means this guy right here is the predominant reaction. Now, because it's the predominant reaction, it's not the exclusive reaction, which means that this one, some HSO3s actually act as a base. They actually do that reaction. So if you throw 1 trillion HSO3 minuses into water, yes, more of them do this because it has a higher Ka, so it reacts a little bit better as an acid. But some of them end up doing what the base is doing. Some of them actually accept H's. It's just that more of them donate than accept. Therefore, what do you think the solution comes out to? Well, the solution comes out to being acidic. Now, is it as acidic as if this thing didn't actually do anything? Well, maybe not. And so the predominant reaction is this guy acting as an acid because it has a higher Ka value. Okay? Now, that's one situation. The amphiprotics, there's always two choices. So for an amphiprotic ion, it always has its acid and it has its base versions. One of those two is going to be predominant, and that's the one that's going to Not that the other one's not happening, but it's the one that happens more frequently, and it's also the one that creates the acidic basic nature of the solution, depending on which one wins, the Ka or the Kb. Now, let's go with one more example here. Okay, so this is the last one where there's a choice. Okay, so you will have a predominant chemical reaction. So I'm going to have NH4 subscript 2 Okay, so the salt is ammonium sulfite. So if I take ammonium sulfite and it's dissolved into water, one, it's soluble, ammonium soluble with a lot of things, so it goes 100%, and so you get 2 ammoniums and a sulfite for every molecule that dissociate. So you've got a whole bunch of choices here, because the NH4 is an acid. The SO3 minus 2, it doesn't have an H, but it is not the conjugate of a strong acid, therefore it's a base. So look at all the options that you have here, okay? Option number 1 is NH4, so I'll write them here. NH4 acting as an acid, so it makes hydronium. And NH3, that has a Ka value equal to whatever the Ka of ammonium is, which is 5.6 times 10 to the negative 11 off the Ka table. So I'm just looking at the Ka table for ammonium. So that's option number 1, is ammonium acting as an acid, giving an H to water. The second option is SO3 minus 2, acting as a base, picking up an H from water to form HSO3 minus plus hydroxide. That has a Kb equal to, okay, so it's Kw. Okay, what I want to do is, because I want to save room here for there's more to this, so I'm gonna go ahead and I'm gonna calculate it. So it would be Kw divided by the Ka of the conjugate acid, HSO3 minus. Kw divided by the Ka of HSO3 minus. The Ka of HSO3 minus is 1.0 times 10 to the negative 7. It's kind of a weird one. So the Kb of SO3 minus 2 is 1 times 10 to the negative 14 divided by 1 times 10 to the negative 7, which is 1 times 10 to the negative 7. Kind of a weird one. Now you might go, well, those are the options. You've got the acid acting as an acid, you've got the base acting as a base. But wait a minute. Who says water has to be the partner in the Bronsted-Lowry reaction? You've got these 2 ions that are free-floating around. Why can't they bump into each other? So why can't the third option be NH4 plus SO3 minus 2? They exchange an H. So the NH4 acts as the acid, sure enough, that's what it is. The SO3 minus 2 acting as the base, sure, that's what it is. And they exchange. So you end up getting HSO3 minus plus NH3. So that is a third option. It's a Bronsted-Lowry reaction. Granted, it does not produce hydronium or hydroxide, but it is a Bronsted-Lowry reaction occurring between an acid and a base. What is the KEQ? Is this the predominant reaction of the 3 choices? Or is it really small? Like, what happens here? Okay, so the KEQ of any Bronsted-Lowry reaction, one of the earlier episodes, the KEQ of this is equal to the Ka of the forward acid. Okay, so the forward acid is the NH4. So it's the Ka of NH4 plus over the Ka of the reverse acid. So forward over reverse. Always forward over reverse. So the Ka of, okay, what's my reverse acid? Meaning which thing from the right-hand side, as you go back towards the left, which of the two chemicals is giving up its H? Well, the HSO3 is giving up its H as it goes back to being SO3 minus 2. So this is the Ka of 1.0. Oh, sorry. Didn't mean to write in the number yet. The Ka of HSO3 minus. The K of the forward acid divided by the Ka of the reverse acid. So that is 5.6 times 10 to the negative 11 divided by 1.0 times 10 to the negative 7. Now, it's kind of a weird one. Okay? Maybe I should have chosen a different example. So we already knew the Ka of NH4. The Ka of HSO3 minus is on the table, and it's right here. And I don't know if you can actually see that, but the value over there is 1 times 10 to the negative 7. Now, it just happens to be the Kb of SO3 minus, but that's coincidental. So the Ka of that guy is 1 times 10 to the negative 7. So that equals, when I do the math, I should be able to do this one in my head, should be 5.6 times 10 to the negative 4. So now you've got 3 Bronsted-Lowry reactions, you've got 3 equilibrium constants, and they've all got relative values. Negative 11, negative 7, and negative 4. So which one's the predominant reaction? Well, the 10 to the negative 4 is the predominant reaction. So actually, whoops, kind of missed that. That is the predominant reaction with a KQ of 5.6 times 10 to the negative 4. So if anybody ever asked you, you've got this salt, ammonium sulfite, dissolved into water. What's the predominant Bronsted-Lowry equation? This is the predominant Bronsted-Lowry equation. And I'll give you a little bit of a hint. Anytime you take a salt and dissolve it into water, if the cation is an acid and the anion is a base, that will be the predominant reaction. The predominant reaction will be with each other rather than with water. So that is kind of a little bit of a hint there. It's always going to be that way. But if somebody wants proof, or someone wants you to say, what are all the different Bronsted-Lowry reactions going on in the water, and which one is the predominant reaction, here are our 3 Bronsted-Lowry reactions going on in the water, and there's your predominant one with some proof to back it up because the KEQs are the largest. Okay? Now, last thing, just to remember, okay, just to remind you of this. If you actually take a solution of NH42SO3, dissolve it into water, this is the predominant reaction. But the other 2 are still happening. Don't forget that the predominant one does not mean the exclusive one. So yes, the majority of NH4s and SO3s are participating in that Bronsted-Lowry reaction. But some of the NH4s are doing that. Some of the SO3s are doing that. And so they're still going on, just not to the same degree as the predominant one. Well, this one produces hydronium and this one produces hydroxide. So actually, this solution is going to be producing a net hydronium or hydroxide, one of the 2, and therefore be acidic or basic. Well, which one is it going to be? Well, you take a look at your KEQs here. The Ka is 10 to the negative 11, the Kb is 10 to the negative 7, which means SO3 minus 2 as a base is going to produce more hydroxide than NH4 plus as an acid. Thus, the net is going to come out with more hydroxide. Therefore, the solution will be basic. So a solution of ammonium sulfite, I would predict it is going to be a basic solution, even though the predominant reaction is the two of them together. Okay, so those are kind of the situations that you may have when someone starts asking you about predominant reactions and hydrolysis of salts. Okay, so we'll see you next time, and this will be the last class for hydrolysis. Next one, we'll be going over the anhydrides. Those are compounds that have, well, they're considered oxides. Okay, so you'll have metallic oxides like calcium oxide, sodium oxide, things of that nature. And you will have covalent oxides, so carbon dioxide, sulfur dioxide, nitrogen oxides, and things of that nature. And what do they do when you react them in water? Okay, so until then, have a good time, and we'll see you later.